An orbital filling diagram is pretty much the exact same thing as the electron configuration, except that it is, how to put this? It's a picture rather than letters and numbers. Although it does include the letters and numbers, but it's more of a picture. And because it's a picture, it shows us some things that the letters and numbers don't. So it can be valuable. So it's the exact same thing. Okay. So for example, we have nitrogen. Okay. Nitrogen is 1s2, 2s2, 2p3. And you can do that as an orbital filling diagram pretty much the same way. 1s, 2 electrons, 2s, but it's 2 electrons, and then 2p. And this is where things get pretty instructive, because of what it shows us about the way electrons go into a sublevel with multiple orbitals. Okay? So it has 3 electrons. Boom. It doesn't really matter which orbital it goes in, but we always fill it in left to right because that's just the way we write things down. In Israel, they might do it right to left. I don't know. I know that they write Hebrew from right to left. I don't know about orbitals, okay, and electrons. Okay, so first electron, second electron, third electron. So this is another rule of Aufbau. E minus go in separate orbitals before pairing. If we're talking about the same sublevel, then electrons will go into separate orbitals before they pair up. Remember, like charges repel. This is still true even for quantum mechanical electrons. All right, so they go in separate orbitals before they pair up. So this is, and the other rule is they point in the same direction. Okay. Again, it's arbitrary whether they point up or point down. We choose up because we're positive. But the thing is, electrons in the same sublevel prefer to have other electrons that have the same orientation. Okay, so it's called resonance. Okay. Electrons with similar neighbors are happier. Okay. They like having neighbors that they share hobbies with, or they share spin with. It makes them more stable. It makes them happier. Okay, so resonance is a pretty big deal. It explains quite a bit, as we'll see when we get to section 5. All right, so let's do some more examples. Let's do iron again. Okay. Iron is 1s, 2s, 2p, 3s, 3p, 4, 5, 6, 4s, and finally 3d. 1, 2, 3, 4, 5, and 6. Okay, so that is the orbital filling diagram for iron. And just as with the electron configuration, that can get tedious for larger atoms, but again, there is a way to simplify this. In fact, it's the exact same way. It is by means of differentiating core versus valence electrons. Okay. Valence electrons are the electrons of the outermost shell. Oops, let's tidy that up a bit. Shell. Okay. So the highest energy level electrons, the ones on the outside of the atom, those are your valence electrons. Your core, let's see, your core electrons equal Ne minus, not valence. So if you have any electrons that aren't valence electrons, they're core electrons. The thing is, valence electrons participate in chemistry. Okay, so they are really what define the properties of our elements. Okay, core electrons just sit there. They don't participate. They don't do anything. They're not involved in chemical reactions. They're not involved in properties or behaviors or any of it. Okay, so this is why we make this distinction. Valence electrons give us a heck of a lot of information. Core electrons, not so much. So, some more examples. Hydrogen, 1s1. It has a single electron. It is valence. Okay, then we get to helium, over on the right-hand side. 2s, oops, not 2s, what am I thinking? 1s2. These are both core. Okay, so noble gases are all core. Okay, noble gases have no valence electrons. That's why noble gases don't really react with anything. Okay, only the valence electrons participate in reactions. Noble gases don't have valence electrons. They're all core. Okay. So now we get to lithium, 1s2, 2s1, core, valence. Okay. So lithium has 2 core electrons, 1 valence electrons. 1 valence electron, singular. Okay, next we get beryllium, 1s2, 2s2, core, valence. We hop on over to the P block. Let's look at boron. Starting to run low on room, I don't really mind, because we can stop after this. 1s2, 2s2, 2p1, core, valence. Okay, so 1 valence, 2 valence, 3 valence. There are a lot of reasons to care about valence electrons. The one we are worried about right now is, just look at this. Lithium, beryllium, and boron all have the exact same core. And that core looks exactly like helium. All of the elements, all 8 elements on the second row of the periodic table, share the same configuration for their core electrons. They have different valence electrons, but they have the same core. So that is how we can abbreviate. Okay? So carbon has its core electrons that look exactly like helium, and then 2s2, 2p2. Nitrogen is helium, 2s2, 2p3. Let's hop down and do iron again. Iron, what is the core of iron? So you look at the periodic table, and here is iron. Its core is going to be the previous noble gas. So we go back, 19, 18. So the previous noble gas, the noble gas that comes right before iron, is argon. So that's the core of iron. Not the nucleus, the core. So argon, 4s2, 3d6. Now, just as we looked at with the when we're talking about how to put together these, electron configurations and orbital filling diagrams and so on, this, even though it's only level 3, still counts as valence electrons. Okay, but we get a complication. Electrons that have a heck of a lot of resonance no longer count as valence electrons. Not really. Okay, so this right here, we're looking at full and half-full sublevels. Okay, but only D or F. That's the important thing. D and F have enough orbitals that you can get significant resonance. Okay, because here's D, say it has a half-full sublevel. This electron here, number 1, it sees resonance with 1, 2, 3, 4. That's a heck of a lot of resonance. Similarly, 1, 2, 3, 4, 5, 6, 7. Okay, with an F sublevel, even half full, this guy sees 6 other electrons that look exactly like him. That's a heck of a lot of resonance. Okay? Whereas a P sublevel, with only 3 electrons, I mean, there's resonance there, but it's not enough. Okay, so this doesn't count as core. This is still valence. Okay. Not core. Okay, but these half-filled D and F sublevels count as core. Okay, sort of. Okay, and a full D or F sublevel also counts as core. Okay, so something that looks like this: 6, 7, 8, 9, 10 is core. Okay.